But hey, Matthew, how are you? Sorry, we missed you.
Yeah, just seeing what's happening here.
Yeah. So as I mentioned yesterday in the lecture, that actually we're giving something about 7 marks out of 60 for the group work. So we need to have an evidence that the student actually communicating with each other and doing the work as a group, because actually group work and the group assignment is a part of the degree recognition by Engineering Australia. If you are going to actually apply for Engineering Australia, they will ask you about the subject that you were doing a group work within. They like to see that. So, and also, when you go to work, the actual work, you're always going to work in a team. It's very rare to work as a one-man show.
Yeah.
So that's why I would like to have all the students be trained on doing the group work. So we will start now with the project again to give a lighter brief about what we talked about last week. 2 weeks ago when I posted the video for the introduction. The video I had was from the lab, and I described the parts physically for the students. And today again to give you a brief about what we had earlier. First, we start about the project in general. And in this project, we need to write down a report about the manufacturing of the power auto gear pump. This is the power auto gear pump. I think there's a timing for the slide. I need to stop this if I can. Okay, do we have... no, we don't have this timing. The problem I have today that most of the university softwares stop working with me, including the PDF. So I will see how to manage that. Anyway, so we're talking about a gear pump. For students who don't know what the gear pump is a pump that instead of using the propeller to push the fluid or the valve and the pressure differences to push the fluid, this one is going to create the pressure differences by having two mating gears moving together. So one side is going to have negative pressure, pull the fluid, and the other side is going to have higher pressure because the two streams on the sides of the pump are going to meet and need to find an escape, and this will be the outlet. It's very popular in the pumping of the hydraulic in most of the hydraulic operated. So whenever you're going to see an hydraulic operated system that have pistons and it's going to be pushed to generate very high pressure, you will find the pump sitting aside near the hydraulic tank. That's including even if you try to check for example, the cranes, which have the stand that pushed by the hydraulic, you will find there's a pump working when they pushing up the stand and taking the crane up. The same thing for the trash collector when they compress the trash. Actually, these two pistons are operated by the hydraulic pump. So you can see for this pump in general, it's made by David Brown Gears. The brand is called the Power Auto, and this model specifically is PUKS 85R. We called 85R because it's capable to pump 85 liters per minute at 1,000 RPM rotation for the main shaft, which is, you can see here the main shaft. This side is going to be connected to a gearbox. The gearbox is going to be connected to a motor. On the other side, we're going to have two ports. One of them is going to be the inlet. The other one is going to be the outlet. We have two models at the lab, but this mainly going to be the model we're going to talk about in this session. If I'm going to explore the pump in general, this will be the part where I'm going to have the main body, the cap. In between them, we're going to have the two shafts. On the shaft, we have the gears, which are going to be the main motor for moving the hydraulic. The shaft, as you can see here, one of them is going to have suppline at the end. One of them is going to be shorter. We call them the lead and the slave, or the master and the slave. The main shaft is going to be longer, have suppline because it's going to be connected to the motor on the other side. We have a set of bearings here. Usually it's going to be the push bearings. It's not going to have any rolling parts. And this push bearing is going to be coated with a Teflon to be sure that it's going to be self-lubricated when we are going to start the drive running. Multiple seals, as you can see here, lip seals, and this to prevent the oil from running out of the pump. These two plates with the H shape, we call them the thruster plates, and these actually were designed to save both the shaft and the main body, because the main body is going to be made by the casting, and this will be a complicated process. The shaft is going to be done by a sequence of machining operation, including the turning, the gear cuttings, and some heat treatment and surface finishing. So it's going to be quite the most complicated part to be made. So why are they running? If we're going to have just the gears in direct contact with the body, we're going to have friction, and this may damage both. So to sacrifice something, we don't sacrifice the shaft, we don't sacrifice the main body. We're putting the thruster plate, which are made of aluminum. We can make them by die casting operation. They're going to be in between to take the load of the friction. Aluminum is going to be, of course, softer material than the steel, so it will tend to wear first. If I would try to overhaul the pump, main thing I'm going to change is going to be the thruster plates. We have a set of dowels, and we're going to talk about the dowels because this is something very important. When you are going to have two mating parts, how you are going to be sure that you're aligning the parts in the right direction? The dowel will do the things. They are barrel-shaped pins. They're going to have very high tolerances, very good surface roughness for the side, and they're going to be inserted in the dowel holes on both sides. And we're going to talk about this one soon. Set of bolts to hold the cap on the main body with enough force to hold them together with the high pressure we have inside the pump. And we have some shaft seals. And this once again to prevent the oil to be running through the shaft outlet. So the material we're using for these parts are for the externals, like the head, the casing, and the bracket. We're talking about the head, the casing, and the brackets. They're going to be made of either the iron, the SG iron, which is the gray iron, the sand gray cast iron, the steel, high alloys, or composites. Now, using this material will depend, of course, on the pressure we're going to have inside and the operating conditions. Usually, the high alloys and the composites are going to be used only if you're going to use it at very high temperature environments, like, for example, the power plants or the nuclear plants. The internal parts, like the shafts here, is going to be made by the steel or high alloys. Again, will depend on the amount of the forces we are going to use for it. The internals, like the gears, here the gears are going to be part of the shaft, so it's always going to be made of steel. The bushing is going to be made of Teflon-coated steel bearings or bushing. So these are the bushing we're talking about. It's going to be sit inside the body, and the shaft will be inserted within. So once again, when we're going to have the motion of the shaft at very high RPM value, the friction is not going to be generated between the shaft and the body. Instead of that, the pushes will sit in between. We made them Teflon coated again because we're operating this pump in a hydraulic. So when we're going to stop the pumping, let's say for 2 or 3 days, the hydraulic will settle down. By settle down, it will leave the bushes dry. So next time when we're going to start up the rotation of the shaft, we may have very high pressure, very high friction, sorry, and this may damage the shaft. So we coat it with the Teflon, so the Teflon will absorb a certain amount of the hydraulic and stay wet all the time. Now, what is the material of the thruster plate and why this material is going to be chosen? Once again, this will be a thruster plate. Thruster plate is made of the die-casted aluminum. Thruster plate is a consumable item and has been designed to wear first. So selecting of the aluminum, because the aluminum is going to be softer than the steel or the cast iron steel we have. for the main body. Why does the pump have to be manufactured to very close tolerances? Now, the main tolerance we're going to have is going to be between the diameter of the gear and the diameter of the bore of the, I will show you that. So the diameter of the gear and the diameter of the housing should be very high close tolerances. Otherwise, we're going to have the pressure loss. Because if the oil will be able to go back, that means we're going to lose the pressure at the outlet. The other dimension which is going to be critical is the dimension of the diameter of the shaft and the diameter of the bushes. The external diameter of the bushes and the diameter of the housing we have down there. Because otherwise we're going to have very tight pressure on the shaft, on the bushes, and this will exert an extra pressure on the shaft and make it work harder, or because it's going to be clushed with the shaft pushes. Now, what will this help us? If I'm going to have very high tolerances, I'm going to prevent the high friction. I'm going to prevent the vibration. If it's going to be loosey, I'm going to have vibration because the part will move with a certain amount of loosey. And we are going to lose the high pressure. We're going to have bad tolerances between the gears and the housing. So the advantage we're going to have here, first, we can achieve high speed. We can get high pressure, no overhang bearing loads, relatively quiet operation, and design accommodated wide variety of the materials. Disadvantage for the high tolerances is going to be for pushing in the liquid area going to be done. No soil is going to be allowed from the side, and fix and clearance is going to be a very critical issue. Of course, to get very high tolerances, this required more complicated and more expensive machining operation. Again, to stop the recording, not recording, I have to stop sharing for a while because I want to get rid of this part at the bottom. Just 1 second. Okay. Okay, now continue with that. Which dimensional tolerances are going to be the most critical? First, the gear shafts. Okay, the gears itself and the shaft sides, the bearings and the dowel positions. Okay, the bearings is going to be inside, the dowel position is going to be these two holes, because this will going to be very necessary for the alignment of the two parts over each other, and the dowels and the bearing themselves. Because we said that the bearings should be freely allow the shaft to run, rotate within, and it should be also easy to fit inside the bearing positioning. The dowels, because the dowels should be fit inside the dowel positions with hand pushing. So we are able to take it out and push it in with very high tolerances. We don't want to have the two mating parts to be fixed over each other, and thus this will require the mechanical forces to separate them while we're doing the maintenance process. How the bearings are going to be lubricated, we mentioned that we are going to have the Teflon coated bearings inside, and thus when we're going to start the running of the pump, a certain amount of the hydraulic is going to be reserved by the pushes on the Teflon layer, and this will keep it lubricated for the next run to avoid what we call the dry running. We have code on every pump, P or W, then we have an O or S, and we have a number, then we have a term like R or something at the end. So the PWO is the power pump series. The O is going to be a rotation direction. Is it going to be opposite to the engine direction or the same as the engine direction? The one we have is PWS. The 90, the number 90 is the amount of the flow per 1000 RPM. So 25 means 23 liter per minute. The 90 is 88 liter per minute. 75 is 74 liter per minute. The one we have is 85, so it's actually pumping 84 liters per minute at 1000 RPM rotational speed of the shaft. Now we're going to have an example on the calculation of the pump flow rate. So we're looking at these equations. Actually, I think that this slide doesn't contain everything, but anyway, we're using the terms common to machine, like the power hydraulic is going to be equal to the pressure difference between the inlet and the outlet multiplied by the Q, where the Q is the flow rate in cubic meter per minute or liter per second. Delta P is the pressure raised across the pump. Q is the flow rate in cubic meter per second. The power of the shaft is going to be equal to the torque multiplied by the omega, where the omega is the angular velocity in radian per second. T is the torque in Newton per meter. We have an example on the calculation of this one, and I'm going to go back to it very soon. Today we are going to study the gear shaft cutting. Now these dimensions are not the actual dimension we have for the shaft for the PWS 85R. This is the shaft we have. The dimension is going to be quite different. As far as I remember, that the dimension for the shaft here is going to be 57. Here is going to be 25. Here we have a 20, and I need to remember the length. Anyway, I have the dimensions available with me, but they are on PDF file. I'll try to solve the problem and get the correct dimension today. Now, usually the shaft is going to be cutted from a cylindrical part. So that's what we have for any shaft. I have cylindrical stock. We start to cut it with the turning operation, remove the layers until we're going to have the final shape, which is going to be as tipping diameters. After that, we're going to cut the gear on the shaft to have the final part. So if we're going to take a look to any cut shaft, I'm going to have this gray box, which represent the cross section of the cylindrical shape. I'm going to have cylindrical shape. I'm going to cut it in half. When I'm going to take a look from the side, I will see a rectangular shape. When I'm going to start to remove the materials in layers, I'm going to end up with that. Let me show you that by using the pen. So this is the envelope of the cylinder when it's going to be cutted by to the side for the side view. So what I'm going to do is I'm going to hold the part from here. I'm going to work on this side first. Then I'm going to turn the part and do this cut second. Because usually the cutting tools are going to be either right-handed or left-handed. The left-handed will look like that. So it's going to be able to cut from the right toward the left. The cutting tool to do the cut from the left to the right is called the right-handed. Usually, there's no machine can do both at the same time. This cutting tool cannot cut this area. So the easiest thing to do is, after we're finishing the cutting from here to here, we flip the part. We take it out of the spindle and we flip it. We hold it from here and do the cut for that part. So we call them as the operation number 1 and the operation number 2. Now, we have some data cutting for the part, like the surface speed for the high-speed steel cutting tool is going to be the 60 meter per minute. That's the feed rate. If I'm going to use the carbide insert, I'm going to use 120 meter per minute. And if I'm going to use the ceramic insert, it's going to be 220 meter per minute. Remembering that this type of the cutting tool can only do the finishing, cannot do the rough cutting. And I think that you remember what the finishing is as well as the rough cutting is. The maximum depth of the cut is going to be 2 millimeter. The feed rate for the roughing is going to be 0.4 millimeter per revolution. And for the finishing is going to be 0.25 millimeter per revolution. The equation we use to calculate the RPM is going to be equal to 325 multiplied by the V, this is the V, divided by the D, which is the diameter. These are the diameters we're talking about. So of course you can see that the RPM value will be varying with the diameter of the part we are going to cut. So at the maximum diameter, we are going to achieve the minimum RPM value and vice versa. We are going to use an Excel sheet to do the calculation of this cutting. And the next sheet I'm going to show up is going to show you how we are going to cut the part by removing the layers, something like you're peeling the part. First layer, the second layer, and so on. So that's actually how we cut the shaft. Now you can see that I set the depth of the cut from one side, but as this part is actually going to be rotate, this one is rotate along the center. So if I get to insert the cutting tool in one side, the other side will be cut because the part is going to rotate. Okay, we're going to learn how to do that in the next slide. Now the rest of this slide is going to tell you about the other machining operation we're going to have for the main body. This main body has been made by the casting operation. We need to work on this phase to do the milling operation. These are the dowels I talked about. These are the dowels holes, and this should be drilled and then reamed. This one should be done on the turning machine or using the standard shaft bar, and we cut it into a length and do some wood surface finishing for the side so it can fit in with the minimum force. These are the holes which are going to be drilled and then tapped. These are this is actually the housing for the gears. You can see, of course, it's going to be done by the casting. We put the pattern, well, sorry, I forgot the name of the part. Anyway, after doing the casting, we are going to have the pre-hole, so we only need to bore it a large diameter. Then we need to do the honing operation to have the exact dimension with the good surface finishing. The same thing is going to be here by the internal by doing the boring operation. We'll be able to have the exact diameter for the seats for the bushes. These are the bushes. It looks like a cylindrical shape, and it's coated inside with the Teflon. This will be the outlet port. On the opposite direction, we have the inlet port. So we have the inlet and the outlet ports. You can see that the inlet is going to be larger than the outlet. The main reason is that the negative pressure is going to be here, is going to be enough to pull the liquid. Here we need to throttle it, so the pressure is going to be higher, and plus we are going to have the required velocity for the leaving liquid. We can make something like a route sheet. You can see that for the studded face, for example, you can say that the operation number 1 is going to be mill the studded face, do the face milling operation. Then the next operation is going to be the drilling of the holes. The third operation is going to be the tapping for the holes, and so on. The raw materials of the part, as we mentioned earlier, this shaft is going to be made of steel. The main body and the cap are going to be made of the gray cast iron. And these are lip seals made of rubber, and this is the truss plate, which is made of aluminum. To make the shaft, we're usually going to use a bar stock. The bar stock have a standard diameters, and we need to look for the diameter which is going to be suitable for our work that required a minimum wastage of the material. So if the diameter of my gear here is 57 millimeters, what do you recommend as the best diameter we use for the stock, for the bar stock?
So could I just ask a question about the lip seals in the previous slide?
Yep.
I was just with the middle one on the left there.
Yep.
Just why I understand that it fits into the piece below, but why would it be that shape and not you know, connect up and be a full circle round, if you know what I mean?
Yeah, you know, because actually what's happened here that we don't have a space here to put it. This will be sitting exactly inside this hole.
Oh, okay.
Yeah, so it doesn't have any space to be a full shape. So we cut it from the side.
Oh, okay. I'm with you now.
And do you know how they formed that shape?
I have no idea.
Okay, they put it in a hard mold. So the rubber is going to be shaped and it's going to be cooled, still having the same shape.
Oh, okay.
Okay. Now, even by the way, for this something like the rubber band you have, if you ever ask yourself how they made the rubber band, the process is very simple. They just put it as a hot latex over the bar shape with a certain diameter. Like for example, if I'm going to put the rubber over this diameter and cool it down, it's going to be hot, then it's going to be cooled down. So it's going to have the same diameter. It's going to be set it to that shape. And then they start to cut by using a very simple machine. If I'm going to put the same rubber over this one, and it's going to be shaped to this diameter, I'm going to have this small thing. Now, actually, the rubber band is exactly like the seal, but the grade of the rubber we're going to use is going to be quite different.
Yeah.
Yep. Okay. Now, thank you very much. Now, we're talking about the diameter of the gear is going to be 57. So what do you think that the most appropriate diameter we can use for the bar stock in that case? Remember that the diameters are going to be 5, 10, 15, 20, 25, 30. Then it's going to increase by 5, 35, 40, 45, 50, 55, 60, 65, 70. After 75 is going to start to increase by, after 80 is going to increase by 10. So 80 is going to be 90, 100, 100, and so on. So 57, what do you think that the most appropriate diameter we need to use to minimize the waste of the material?
On it for 57.
Yep.
Yeah, wouldn't it? Is it less than 57?
No, it should be more because actually, if I'm going to cut the gear, for example, is going to be smaller than the original diameter because we are going to remove some material from the side.
Yeah.
So,
Yes, of course.
So the best diameter we can have is, yes?
Around 60, 65, around there?
60. Because in the 60, you're only going to remove 1.5 millimeter from the side. And this will mean you reduce the diameter by 3 millimeters, and you will get the exact diameter. We're going to talk about the length of the spot, the mass of the spot, and how we can calculate the wasted material by the cutting operation soon. Once again, we need to connect the shaft to the gear, to the gearbox on the other side. So we need to have the supply at the end, and this is the gear on the side. Usually the supply is going to be cut by the approach cutter. You remember the approach cutter is a cutting tool. If you're going to take a look from the side, from one side is going to be straight, on the other side is going to have a multiple teeth, which is going to increase by grade over each other. This should be here. Okay, so just keep increasing in the diameter. So what's happened is when I get to pass this cutting tool over this shape, the last cut is going to have that material to be removed. So we just pass it slowly. You can see that we have multiple approaches, and we're going to generate this supply and cut. For the gear shape, we have to do it by cutting operation of the gears, which can be done by multiple operations, including the milling cutter. This is what we call the gear milling cutter. That's the operation. The shaft is going to be fixed on what we call the indexing tool, and it's going to keep rotate and the cutting tool passing it through and having the multiple cutting of the teeth. These are other operations. We can do it on the CNC machine if we're going to have the 5 axes, or we can do it by the gear hopping operation. This operation is going to be very useful if we're going to have the mass production, because this machine is going to be specialized for the cutting of the gears, while this one, we can set it on any milling machine, and the milling machine can do the job. The grinding process is very necessary because we need to have very good surface finishing for the gear teeth. Otherwise, the gear teeth, again, while they are going to be meeting, they are going to have very high friction, and they start to what they call stuck with each other. So we need to do some grinding for the gear teeth, as you can see here. This is a special grinding wheel for the gear teeth. And also the shaft itself required to have a grinding operation for the cylindrical shapes to have the good surface finishing that prevent it from having high friction between the shaft wall and the internal wall of the bushes. After we finishing with all the operation, we need to do the final inspections for the dimension of the part. And this is one of the examples. We can use the CMM machine to do that. And we have another machine similar to this one exactly, which can check the surface roughness of the gear teeth, because these are going to be a critical points. After we having all the parts to be done, we can assemble the parts of the gears and the gear pump to have the final production. After the assembly process, and this will be very important, you need to mention about for any product you are going to make, you need to make the final inspection of the assembled pump. Now, actually, the process of the inspection of the gear pump is not that hard, but it's not that simple. The first thing we are going to do is we are going to close the pump. We are going to close the this side and one of the inlet or the outlet. Usually they close the outlet, and they start to pressurize it with very high pressurized water, and then they lock it. They lock it for something about 24 hours. Increase the pressure gradually and see how much pressure that the case can have before it's going to be shattered or the pump is going to be leaked. This will be the first test. The second test we have is just get one of the pumps and run it at the maximum allowable RPM value and keep it running for 2 hours and check if it's going to be filled or not. That's for the inspection of the pump itself. Usually the inspection of the prototype is going to be run the pump for 10,000 hours. 10,000 hours. Because usually you will understand that when you do any testing for the vibration or the failure test, we call it the failure test, we run any product we're going to have for 10,000 hours. If it's going to pass the 10,000 hours of operation without any failure, that's been it's good. Now, some of the questions are available for you in the sheets. I'm going to show you the sheets now. This will be the sheet number 1. The sheet number 2 is the material wastage when the machining of the driver gear. And I'm going to do this one today. How we can calculate what is the amount of the material has been lost during the machining operation of the gear shaft. Next week, we're going to do some, actually, this will be done today as well. Okay, I'm going to show you how to do that on the paper. This will be the worksheet number 3. This will be for next week. Okay, and then we're going to have how to write down the report. The report for this project is going to be due at the end of the week number 11. But in all the cases, as you know, usually we're going to have an extension for that because we're still working on the assignment number 2, which is the hand tool project. I know we're doing that for the first time. So we are not building actually the real pump, but still we have too much work to do because this is the first time we're having the project in this shape. Now, if we go to the canvas, you will find the multiple slides available for you. The first slide is going to be about the data operation. I covered that in the lecture already, so this will be just for your revision. These are the three operations. The most important thing for us is going to be the turning operation. Now, in the turning operation, we're going to have a single tip cutting tool. This cutting tool is going to be moved multiple times over the part and start to remove the material to have the final shape. The cutting tools, we said once again, this will be for the actually this one is called casing, made by the Carbide insert cutting tool, and this one made from the high-speed steel cutting tool. This can do the counter cutting. This cutting tool, you can see, is coming from the right to the left, so that we call the left-handed cutting tool. This can only cutting by moving from the right toward the left. This cannot do it the opposite way. The chamfering cutting tool, when it's going to be cut by the side instead of the tip. The parting or the grooving cutting tool is going to be straight cut. It's going to cut from this direction to separate the two parts. We're not going to use this one actually in this operation. We can have a cutting tool to do the threading, which is generating of thread on the shaft, and we don't have, once again, this operation in this project. Now you can see these are the cutting tool. We have the right-hand cutting tool, cutting from the right to the left. We have the left-hand cutting tool, which is cutting from the left to the right. Usually, we cannot have both cutting tools on the same setup, but we have different types of the machining, which called the twin spindle, and I'm going to show you that on my slide next. Okay, now we go to, yeah, I'm going to show you this slide, and I'm going to show you how we do the calculation for the speed of the cutting and the time required to perform the cutting on the shaft. This will be the calculator. It's an Excel sheet. You can download it. The only thing we need to change is going to be the original diameter of the part here, and then everything will be calculated for you on the other side. Okay, so we're going to post a video on how to use this calculator. Actually, I think I can have it here directly. If I go to my channel, yeah, I will go to the studio. Okay, so because actually this will save the time today for explaining the this calculator. And
Yeah, I hear you. I think you've got yourself a new subscriber.
Ah, actually, it's a free channel, so I don't worry about that. Okay, so that's the video we have. Because they don't pay me anything for these ads, because I said my channel as educational, so it's all free. Anyway, I'll post this one here, and again to post the same link on the main page. Yeah, this will show you how to use this calculator step by step. Now, what we're going to do now is going through this presentation, and I'm going to show you how we can do the calculation for the removal of the materials. Again, the process is going to be quite simple. We have the shaft, and we start to use the cutting tool to remove the material by moving from the right to the left. So each time we insert the cutting tool inside the shaft, we're going to set what we call the depth of the cut. The depth of the cut is usually going to be in terms of the radius, but actually it's going to be when the machine is going to read it on the CNC machine, or it's going to read as a diameter. So that's the shaft. Oh, again, I don't know why that each time I do the presentation, I have the same problem. Sorry, just give me 1 second. push again. Okay, now we can see that the two shafts in front of us, just to remind you once again that this shaft has been made by using this torque bar. We got this torque bar which have a cylindrical shape, and we start to cut them down until we're going to have these 3 steps. And then we do the supplying cutting and the gear cutting. Now, mainly what we're going to doing today is discussing the cutting into multiple cylindrical diameters. Because once again, the supply cutting is going to be done with another operation, and the gear cutting is going to be done with another operation. I do have some video which can help you a lot on writing down these 2 operations on your report. So once again, these diameters are not going to be the correct one. I do have the actual diameter of the shaft we have, and mainly as long as I remember, that the diameter we have here is 57. It's not 77. This sheet was done as an example. It's not the original one. And I think this one was 25, and this one was 20. Okay, so these are 3 diameters. The thing I remember is that the total length here was 202 millimeters. 202 millimeters. Now, I will leave you to think about if the maximum diameter is 57, the maximum length of the shaft is 202. What is the suggested diameter and the length of the stock bar you are going to use for your operation? Just write down this one, and I'm going to connect the camera so I can show you the translation process on the paper while you're doing those adjustments. Stop that. Here's my again. Yeah. Okay, so let's get that on the paper. We said that the maximum length of the shaft is going to be 202. So definitely I'm going to leave some extra material on each side to be removed by the facing operation. So the stock bar is going to have the length of at least 206 millimeters. The diameter, 60 millimeters. Now, my shaft, it will be sitting in between this shape. So I will make it as sections, but actually they're going to be connected together. Of course, these should have the same diameter. I'll just do it roughly. Okay, so the shaft will be sitting in between. So the hatched material is what we're going to remove. Now, I would like to check what will be the amount of the removed material in mass. Do you have any suggestions on that? If you check the lab sheet, it suggests to do the following. Take the gear, put it in a water, and check the amount of the water being increase in the skull, and then you will know what is the volume of the part we have here. And we can check the volume of the material by doing the basic calculation of, we have a cylindrical shape. The diameter is 60 and the height is 206. So we can get the volume of this one, right? It's the area of the diameter multiplied by the height.
Mm.
Now, is it possible to get the shaft and put it in the water while you're working in the lab?
No.
If you don't have the scale container, you cannot do it. Easiest way to do that, we all know that the volume is equal to the density, the mass is equal to the density multiplied by the volume.
Mhm.
Okay, so the volume is equal to the mass divided by the density.
Yeah.
How to get the mass?
We use the materials thing, the weight of the
mass.
material. Yeah.
Yeah, how we can get the mass? Yeah.
Well, you'd have to find the volume of the cut, wouldn't you?
How to get the mass? If I'm going to have this pen, I would like to know what the mass of it.
The mass of the cut or the original clock?
Well, the mass of this pen. How can I get the mass of this pen?
Measure it.
The scale.
Yeah, put it on scale. We got that. Now, the density. Use tables.
Mhm.
Because every material has its own density. Density of the steel we're using for this shaft is equal to anything between 7,200, 7,800 kilogram per cubic meter. Now the mass is 1.577. I weighted that already. 8 kilogram. Now I can find the volume. Yeah. Done. We got the volume of the shaft. Now, the volume of the stock is going to be the area multiplied by the height, which is going to be the area is for the stock. The 0.206 multiplied by the pi multiplied by the 0.06 squared divided by 4. So we can find the volume and then the wasted material. Volume is going to be equal to the V stock minus the V shaft. Done. Okay, so this is the basic calculation for the volume of the wasted material. Then you can do the percentages. I would like to find the mass of the wasted material. I will multiply that by the density. I think this point is clear. You need to sketch that shape. You put your dimension on it, whatever the dimension you're going to choose. This is going to be the one available on this slide or the original one I will going to send to you soon. All good for that point?
Yeah.
Yeah.
Is it clear? Okay.
Would you use the diameter or the radius for the sphere volume? I mean, for the cylinder
Cylindrical volume. Well,
it's always radius, right?
Yeah. No, it's always radius if I'm not going to use divided by 4.
Yeah. Okay.
Yeah.
Fair enough.
Yeah. Right. So the two equation we have is up to you to use the easiest one. The area of the circle is either pi r squared or is going to be equal to the pi diameter divided by 2 square, which is going to make it square divided by 4. I'm sorry, I'm going down here. Yeah, it's going to make it same thing, diameter squared divided by 4. Well, I don't know why I'm using this one because most of the other subject I'm teaching
Wait, wouldn't the
using
D
this one.
wouldn't the D also be squared? If
Yeah, of
you
course.
so that
Yeah,
means
if I get to square that,
yeah.
we're going to end up with a pi d squared, and the 2 squared is going to make it 4. That's my thought.
Wait, I think I didn't see this 0.06 squared. I didn't see it in the from the
Oh,
screen.
yeah, sorry.
Oh
It's,
yeah,
it's
yeah, I see
squared
it.
here, very small one. Yep, sorry for
Yeah.
that. Okay, so now I will leave this one for a while so everybody can see it later and take a snapshot of it and use it for the calculation. Once again, density is going to be your choosing. Anything between 7,200 and 7,800 is going to be correct. They have different standard for the alloy we have for the steel, which is important in the shaft. Now, this very important thing, the shaft is always going to be machined out of stock. If I was the marker, and actually I did that before, when I was the marker at the stages of this report back in 2012, if the student write to me that the shaft is going to be made by 3D printing, okay, or casting, this has nothing to do with the logic of engineering. It's wrong. It's always going to be machined of stock material. Now we go back to the shaft. That's what we've done. We know the dimension, we know the diameter, we did the calculation. The dark gray is going to be the left material, and the light gray is the removed material. Now we go to the operation. We said that we're going to cut the part as 2 stages, the operation number 1 and the operation number 2. Now, why we need to do that? Because in the first operation, we need to hold the part by using the jaw form here, the jaw of the milling machine, turning machine. And we start to do the cut on everything by cutting from the right to the left by using the right-handed cutting tool. And then we can flip it, hold from the other side, and start to cut from the other operation. Some of the cutting machines, turning machines, have what we call the twin spindle. We always remember that when we do design for manufacturing, we always try to use the machines we already have. Don't try to order a machine for a single job. So the first operation is, just remember that the cutting data, because it's going to be required for your further calculation, we need to calculate the RPM value. So the RPM value is going to be given by the equation that the N, which is the RPM value, is going to be equal to 325. This is shorthanded equation, multiplied by the speed of the cutting, divided by the diameter. Now, that's mean when we are going to cut at larger diameter, the RPM is going to be less than cutting on the small diameter. One of the main reasons is what we call the arm of the force. You remember the cantilever theory, that if I'm going to have a longer arm of the force, the effect of the force is going to be higher if I'm going to have the shorter one. So this force is going to be affected on the cutting force we are going to use for machining. That's mean at the higher diameter, we're going to have more resistance for the part, and thus we're going to consume more energy. So it's much wiser to work slower, and thus we're going to reduce the torque of the cutting tool. This is something we need actually to cover in this subject, but the only chance I can do that is going to be through the practical sessions. Hopefully, starting from 2022, we're going to give that as a calculation equations. I don't know if you think that you just missed it or you just skipped it. It's up to you how to think about it. But this subject totally is going to be developed next year. And the student actually not going to have the hand pump. Instead of that, this project is going to be the only project, how to build a gear pump. Well, I know I think you missed it because we're supposed to have too much experience from that. Now, the cutting tool material will decide what will be time of the machining required, because every material have some specification which make it stronger and actually more resistance to the heat generated due to the friction. So you can see that the high-speed steel is going to have the maximum velocity among the other cutting tools because it's highly affected by the friction. And the tool life will be simply shorter at the high speed. So the maximum cutting speed we can get for the high-speed steel is going to be 60 meters per minute. The carbide insert is 120 meters per minute. And for the ceramic turning, it's going to be 220 meters per minute. Again, just to remind you that the ceramic cutting is not strong enough to cut with high depth. So we usually leave it just for the finishing operation. The maximum depth of the cut is 2 millimeters. That's for the rough cutting. And it's going to be something between 0.5 to 0.75 millimeters for the finishing. For the feed rate, what we call the F value, and this will be actually very useful to find out what will be time required for the machining in revolution per minute. The roughing is 0.4, the finishing is 0.25. So we start to remove the first layer. So again, to put on the Excel sheet that this operation is roughing operation. Depth of the cut, we want to remove for this example, from 81 to take it down to 77. So what will be depth of the cut? Depth of the cut is the depth of this blue strip. I want to remove 3 millimeters from the diameter. So how much I'm going to set the cutting tool inside the work from one side? Any clue?
For one side.
Yep.
Would be 1.5 mil.
1.5 mil. Okay, 1.5 mil. Because depth of the cut is going to be difference in the diameters divided by 2. So it's 80 minus 77 divided by 2 is 1.5. Now the length of the cut is going to be all the length from here to here. Because this will be my first peeling. I'm removing 1.5 millimeter depth. That's means I'm going to reduce diameter by 3 millimeter. I'm going to move all the way from the beginning till the end. So the length of the cut here is 200 millimeters. Once again, these numbers are not correct. Now the feed rate we're going to use, this is roughing. The depth of the feed rate is going to be 0.4 millimeter per revolution. For the high-speed steel cutting tool and the carbide insert, we have different velocity of the cutting. Usually, that's what we call the radius of the insert, 0.8 millimeter. For the roughing, this cutting tool can make 0.4 millimeter per revolution. For the finishing, we're going to have 0.25 millimeter per revolution. So the feed rate is going to be 0.4 because this is roughing operation. The speed of the cutting, now we need to divide the table into the carbide insert, the high-speed steel, and the ceramic to calculate what will be the speed of the cutting for the 3 different types. So now you remember that the carbide insert and the high-speed steel can do the roughing, but the ceramic cannot do the roughing, so we're not going to have any table for it. So we put 2 speeds here. The first one is going to be based on the V value of the 60 meters per minute. So the RPM is going to be equal to 325 multiplied by 60 divided by the 77. And this will give me that the RPM value is going to be 253. For the carbide insert, 120 multiplied by 325 divided by the 77, and this will be equal to 506 revolution per minute. Now we need to calculate the high-speed steel time and the carbide insert time. If the RPM value depends on the diameter, what does the time required for the machining will depend on? If I'm going to drive from here to Newcastle, the distance is known, let's say 250 kilometers. If I'm going to drive at 200 kilometers, oh, well, that's too much, 120 kilometers per hour, are going to be there in 2 hours. If I get to drive to an area which is 500 kilometers at the same speed, is the time going to be longer or shorter?
Longer.
So the length of the cut is going to be the same, the first parameter that decide what will be the time of the machining. The second parameter is going to be the feed rate. But the feed rate is not going to be this one. We have another feed rate, which is called the linear feed rate, which is the velocity of the cutting tool in this direction. The FR is equal to the RPM multiplied by the feed rate we have. So now we have the RPM value 253 multiplied by 0.4. This will be the FR. This will be the velocity in millimeter per minute. And the distance is known. So the time is going to be equal to the distance. I should put L here. The distance to be traveled multiplied by the value of the feed rate. This one is in millimeter. This one is in millimeter per minute. So we're going to end up with the time in minutes. Multiplied by 60 is going to be in seconds. So that's what we have. The cutting time is going to be length of the cut divided by the feed rate multiplied by 60 to change to second. So we calculate both times for the high speed steel, and the carbide insert should be half the time required for the carbide speed because the feed rate is going to be doubled. So we keep doing that. Now the next cut is going to be just from here to here. We need to do it in multiple times until we're going to reach this diameter. So the next rows is going to be next cut 2 millimeters, 2 millimeters until we're going to reach the diameter of the shaft here. Then we're going to have another rows for 1, 2, maybe 3. I'm not sure about that. Okay, and done. So that's what we need to calculate. After we're finishing all the rough cutting, we need to do a finish cutting. The finish cutting will start from here and ending at here. And that's what we're going to discuss later. So the length of the cut is going to be 1, 2, 3, 4, 5, 6. And that's what we're going to do like that. So, yep. So we did roughing until we're going to finishing the shape of the part. And then we do the finish cutting to finalize everything. The finish cutting, we calculate the length of the cut, which is going to be equal to the radius here plus the length, plus the difference in the radiuses, plus the length, difference in the radii and the length of this part. And thus we're going to find the total length here. The cutting time is going to be length of the cut divided by the feed rate multiplied by the RPM. Now here, we're going to have 3 values because one of them is going to be for the high speed steel. The second one is going to be for the carbide insert. And the third one is going to be for the ceramic. Sorry for the bad writing here, but it's actually too hard to write with the mouse. So you can see here that the last depth of the cut is going to be 0.6 millimeters, can be 0.5, whatever the number is. Length of the cut is 213.5. The feed rate is going to be slowed down. The RPM value is going to be slowed down because now the feed rate has been changed. Sorry, the velocity of the cutting has been changed. And thus we are going to have the times required for the cutting is going to be, of course, longer because we're starting here with lower feed rate until we're going to finish the cutting. Now here we come to the ceramic insert. We said that this ceramic insert are going to have a higher speed of the cut, but they are not suitable for the rough cutting, but they are very good for the finish cutting. So we're going to add them here as the time required for the finishing operation by using the ceramic insert after calculating the RPM value required for this operation. Then we're going to have the total times in minute. Now, the times we're going to have are going to be 3 times. The first time is by using the high-speed steel for the finishing and roughing and the finishing. The other time is going to be for the carbide insert for the roughing and the finishing. Now we're going to have another 2 times. The other 2 times are going to be the high-speed steel for the roughing, plus the finishing with the ceramic insert. And the 4th time is going to be the roughing with the carbide insert, but the finishing with the ceramic insert, and done. Now, some examples about the machining operations in general. Need to remove that. The problem we have is that you're not going to hear the voice. I'm not sure it's going to be actually important to hear the voice, but you will see these are the turning operations. Okay, so you can see this will be a turning operation, and this will be the finishing operation. You can see start from the face till the end. Now this will be the first operation. We're cutting anything to first half. You can see after they're finishing, they're going to do the cutting of the part. Okay, they will cut it, and they will take it to the other spindle here. You can see this is the other spindle. So the other spindle is going to hold it from the other side. Again, this is twin spindle machine. You don't have to order your machine for a single job, unless if again to invest the machine for other things, because the setup time, or we call the inventory cost, is going to be quite expensive. And usually we use what we have instead of try to getting a new inventory for your factory if you're going to have a new product. By the way, this is the drill machine, which can do something like strip line cutting. Try to search this video. Actually, I don't know if the link is still available on YouTube, because we tried that yesterday for one of the operation and we couldn't find it. Okay, I think that the most important thing for me, trimming, and then we're going to do the work on the other shaft for the operation number 2. Now we're going to start to work here from the left to the right. You can see that actually another part is being under processing on the other side. This is its twin spindle machining center. It's quite expensive, so we usually try to avoid using this one in our project, but it can be given as the alternative machining processes or the suggested machining processes. What's that video is? Cutting all the supply. I think that the voice is going to be available in the video later, but you cannot hear it at the moment. Now, this is what we call the drive shaft, which is a part that's connecting the gearbox to the wheels in the front wheel drive cars. And usually this part is going to be subjected to very high rotation force, and at the same time some non-axial forces, because it's going to be connected to the wheel. So as the wheel is going up and down on the road, this will be damaged very fast. In this operation, he making a costume part, spare part that's not actually available in the market. So he's going to cut this line here. You can see this cutting tool is called the dovetail cutting tool. The most important thing for me is to show you what we call the indexing tool. Okay, so this is a cutting tool. It can cut gears and cut supply. Okay, that's what we call the indexing tool. This indexing tool is divide the circle into an equal divisions. So for example, if I would like to have 5 teeth on my gear, again, to divide the circle into 5 divisions by using this indexing tool. So I will put the shaft on the first division, cut the gear or the supply, then I will take off the machine, turn it to the next position, and cut the other one. Again, to have 5 positions, and thus again to have 5 gears to be cut on the shaft. Here they're cutting this supply, so I just want to show you how they're going to rotate the indexing. So he just turned the thing and it's going to cut the next supply. Now, similar cutting tool can cut gears as well, but of course, going to be a little bit larger than this one. So as you can see here, turning to the next cut, next position, and start the cutting. Until again to have the whole cut to be done. And now the part is ready. It's already being cut. Okay, so that's it for today. The video, once again, is going to be available on the main page for the subject. If you still have any question, you can come back to me. What did you learn today?
Lots and lots.
So sorry for putting all the materials actually in one session, but just remember that everything we learn here, this can be also used in any other things like the other project, which is the pump. Also, it can be applied to future subjects like the one that require you to build something. Now you are equipped with some of the knowledge that's going to help you to know how the things are made. And that's why actually today I have you can notice actually that's available on the Teams page for this subject. I put something about the investing casting for the large well, this can help you actually because anything can be done with the investing casting. And also one of the students, I'm not sure who he was, he said, okay, now we can actually 3D printing the pattern for the investing casting. I told them usually they're doing the injection molding, the wax casting, because you would like to do it in massive production. So the best way to do it is have the mold injected with the wax, leave it to solidify and use it directly. Unless if you're going to do it as a pattern for a single time using. And then you can do it with 3D printing. This will be acceptable thing. But one of the main problems we have that once again, the surface is not going to be good enough. So we need to do some extra processes to remove the stepping of the sides with 3D printing operation. So I'm not going to keep you a lot. I think that this should be enough for today's session. I'm going to run another session in 10 minutes for the other group. I don't know if they didn't show up. I'm not going to run it.
Yeah, I think it's not in the, or at least for my timetable, today's class